Hi everyone, and welcome to this introductory tutorial on HPX. My name is Dimitra, and today we'll go over what HPX is, why one would like to use it, and the key principles that govern it. At its core, HPX is a highly efficient threading implementation. Compared to standard threads, or P-threads, HPX provides significantly lower context switching overhead and scheduling latency, often improving performance by 2 to 3 orders of magnitude. On top of this efficient threading system, HPX implements several functional layers. First of all, it provides a full implementation of C++ standard facilities for threading and concurrency, including equivalents of std_thread, async, future, mutex, etc. This means that if you have C++ code using these, you can simply change the namespace from stud to HPX, and in most cases your code will run faster without any additional modifications. HPX also offers a complete implementation of all parallel algorithms mandated by recent C++ standards, including C++ 17, 20, and even the latest additions in C++ 23. It also extends these algorithms with additional features such as asynchronous execution, parallel range-based algorithms, and vectorizing execution policies such as CMD or parcmd. HPX also provides a full implementation of the senders-receivers model, a feature currently being discussed for standardization in C++. This implementation is built using C++ 17 and helps simplify asynchronous programming and task composition. It also extends standard C++ parallelism interfaces to work on tightly coupled clusters and supercomputers. It provides a global address space, load balancing across multiple nodes, and a uniform API for both local and remote operations. If not already convinced by all these reasons I just mentioned, let's see why you should consider HPX for your projects. HPX is designed to overcome the fundamental performance bottlenecks in parallel and distributed computing. These challenges can be broken down into 4 key factors. Starvation. This occurs when there isn't enough concurrent work available to keep all resources like processors and threads fully utilized. HPX helps by dynamically balancing workload distribution to prevent idle resources. Second of all, we have latency, which includes delays that occur due to time-distance constraints when accessing remote sources or services. HPX mitigates this through advanced scheduling and execution policies that reduce wait times. What about overhead? Managing parallel tasks and resources introduces additional work that is not necessary in sequential execution, and HPX minimizes this by optimizing task scheduling and reducing synchronization costs. Finally, we have contention. Many times when multiple threads try to access shared resources, they may experience delays due to resource oversubscription. HPX employs fine-grained parallelism to distribute workloads more effectively, reducing thus bottlenecks. Now that we know the performance bottlenecks HPX is designed to overcome, let's have a look at its governing principles. HPX is built around several key principles that differentiate it from traditional parallel computing models. First principle: latency hiding instead of latency avoidance. While it's impossible to eliminate all latencies, HPX focuses on hiding latency by keeping the system busy with useful tasks rather than waiting idly. This is similar to pipelined execution in modern processors or asynchronous input-output operations. Second principle: fine-grained parallelism over heavyweight threads. Instead of relying on coarse-grained parallelism with large, heavyweight threads, HPX encourages breaking tasks into smaller units that can be scheduled more efficiently. Another principle is constraint-based synchronization instead of global barriers. Traditional parallel programs rely on global barriers, forcing all threads to synchronize at certain points, often leading to inefficiencies. HPX instead employs constraint-based synchronization, allowing tasks to proceed independently when possible. Another principle is adaptive locality control instead of static data distribution. HPX dynamically adjusts data placement and execution location based on real-time workload conditions. This results in better resource utilization and lower communication costs in distributed environments. Moving work to data instead of moving data to work. Rather than transferring large amounts of data between computing nodes, HPX moves computational tasks closer to the data. This reduces costly memory transfers and improves performance. And last principle for HPX is message-driven computation over message passing. Instead of explicitly managing message passing between different parts of distributed systems, HPX uses message-driven computation. This allows for more efficient communication and reduces the complexity of writing distributed programs. In this tutorial, we introduced HPX, its advantages over traditional parallel computing approaches, and its governing principles. By leveraging an efficient threading model, full C++ standards compliance, and innovative scheduling techniques, HPX enables high-performance parallel and distributed computing that scales efficiently across multiple cores and nodes. In upcoming videos, we'll dive deeper into how to get started with HPX, parallel algorithms, vectorization, futures, task scheduling, distributed computing, and many more. So stay tuned for the next part, where we'll guide you through setting up HPX and writing your first parallel program.